So here we go with chapter 10. It's the last chapter. It's on gases. We're almost there. We're going to start with the properties of gases, which we've talked about some of these already in chapter 3. But this should be kind of a combination of, I think I heard that before, and potentially some new things. So these are the 5 properties. I'm going to go over them in a little more detail, so don't worry about getting this slide down right now. I have each of them on a slide already. So let's go over them. The first 2 properties, we're going to talk about the shape and the volume of gas. Gases take the shape of its container. So if the container is very big, then the volume is going to be very big. If it's very small, the volume is going to be small. Whatever shape the container is in, that's what it's going to be in. For this to happen, gases have to expand and compress. So the second property is that gases expand uniformly. So when they expand, they increase their volume. They can be compressed as well. That's just the property of a gas. Leading us to number 3. Gases compressed uniformly. So if you smush them together, eventually you'll form a liquid. And I believe that the bullet points on these are switched for compression and expansion, so I'm going to fix that. So with compression, you compress until you form a liquid. With expansion, the volume will fill whatever the container is. If you have an expandable container, it will continue to fill that volume. So I will fix that. Don't worry about it. The 4th property, gases have a low density, which means, go back 1 slide or to the very beginning with the list of all 5. Okay, yeah, we can go back. So gases have a low density. That means that there's not a whole lot of particles for any given volume. And just to give you an idea, the density of air is 0.001 grams per milliliter. The density of water is 1 gram per milliliter. So, big difference. Very low density. Now go back 1 slide as requested. Let me know when you're done. So I forgot to mention, there's no chapter 10 video yet. I will be recording one and putting one on YouTube. So it's not just going to be the live lecture, but you'll also have the regular pre-recorded video with everything all prettified. I just didn't get an opportunity to do that yet for hopefully obvious reasons. Okay. So the last property is that gases mix uniformly with other gases in a container. So air, as you know, is a mixture of gases. We've got nitrogen, we've got oxygen, and a bunch of other stuff. And all of those things mix together uniformly. You don't find one big pocket of oxygen over one place and one big pocket of nitrogen somewhere else. If you have a mixture of gases in a tank, like if you were to go scuba diving, which I would never do in my life, but some people do it, you might have a mixture of oxygen, helium, and nitrogen gases, and they're all mixed uniformly in that tank so that every breath has the same composition. You're not going to get a little bit of oxygen here, a little bit of helium there. Next time it's sprinkled in with some nitrogen. It doesn't work that way. It's a homogeneous mixture. That's the properties of the gases. Test questions would be multiple choice, just to see, okay, which one is a property of gases, which one isn't. Does that make sense? So that's kind of the expectation here. Let me know if you're good with that and ready to move on. Okay. Now we'll talk about pressure. So pressure in general is the result of all those gas molecules moving all around and striking the walls of their container. That's the pressure that you can measure. As you increase the temperature, those gas molecules start moving more quickly, which means they're going to strike the walls more and more often and with greater force. So you're going to increase the pressure as you increase the temperature. We will revisit this this trend or this relationship when we talk about the variables that affect pressure. But right now, we just want to introduce pressure as being the result of molecules striking the walls of their container. Atmospheric pressure specifically deals with the air molecules in our environment. So all the oxygen and the nitrogen and the carbon dioxide and all those other things that make up the air we breathe, they're exerting atmospheric pressure. And there's a man named Evangelista Torricelli who invented the barometer to measure the atmospheric pressure. Now, I think the Weather Channel still exists, but when I was a kid, we didn't have internet. We didn't have a smartphone to just whip out and say, and ask it, what's the weather? Is it hot outside, Siri? Like, that didn't exist. You had to watch the weather or listen to it on the radio. So there was a channel, the Weather Channel, dedicated to weather 24/7, 365, which sounds absolutely ridiculous because it is. And part of that weather report was the barometric pressure. That tells you what the atmospheric pressure is at that time. The pressure in the atmosphere changes when the storm systems change. If it's sunny versus rainy versus cloudy. Not very big changes, but big enough to measure. And so what Torricelli did was he created this vessel where you have this tank that has liquid mercury in it. So that's what this gray stuff is. It's liquid mercury. And there's a glass tube. So the tank is open to the atmosphere. The pressure from the atmosphere pushes down on the mercury and causes the mercury to go up the glass tube. You can read and measure the height of the mercury in the tube, and that measurement is the atmospheric pressure. On a normal good day, atmospheric pressure is 760 millimeters of mercury exactly. So when we do calculations coming up, that's an exact number. And it's literally millimeters of mercury. That's what you're measuring here. The number of millimeters. We can also talk about atmospheres and torrs, and there's other units for pressure that I'm going to introduce in a second. But that's how a barometer works. You're going to need to understand that for your exam. Just the basics. That the atmosphere pushes down, pushes the liquid mercury up the tube. You read that level. That is the barometric pressure, or the atmospheric pressure. We good so far? Okay. So as you can see, there's a table here with all types of pressure units. Atmospheres, inches of mercury, centimeters of mercury, all this stuff. You don't need to memorize it. The ones that we'll be using in class most frequently are these. The ones that I put a star next to. If you end up taking physics, then you'll likely see pascals. You may also see PSI. So I just want you to be familiar with those. But again, do not memorize this table. You will get this information. The reason that I'm giving this to you is because we can convert from one unit to another for pressure. So I'll do an example for you. Let's say the barometric pressure is 26.2 inches of mercury. What is the barometric pressure in atmospheres? If I were giving you this question on an exam, I would tell you 1 atmosphere is equal to 29.9 inches of mercury. I will not tell you that the 29.9 is an exact number. You'll need to know that. This looks strangely like a unit equation. That's because it is. Whenever we have a unit equation, we can write unit factors. So we'll have to use one of those to convert from inches of mercury to atmospheres. Which one am I going to use? If I want to figure out the number of atmospheres, am I going to use A or B? Yeah, we're going to use A. And unfortunately, that break might have to come sooner rather than later because this child is waking up. He is not bottle fed, so I apologize. What you would do for this is you would take the 26.2 and divide by 29.9, and that will give you the number of atmospheres represented. You can put that in your calculator and let me know what you get. That's exactly what I got. You should get 0.876 atmospheres. We're using 3 sig figs here because the information we were given in the problem has 3 sig figs. And that 29.9 inches of mercury, we're treating that as an exact number. Questions here? I'm going to give you your own problem. Well, let me know. Do you want to do a problem like this, or do you want to keep moving on? Okay. So I will include the answer for this one, but I always have it. When I have it, then y'all don't want to do it. If I don't have a backup question, then y'all want to do one. But that's all right. Every class is different. So moving right along, we introduced the concept of gas pressure. Now we'll talk about the variables that affect gas pressure. We've got the volume of the container, the temperature of the gas, and the number of molecules of gas in the container. And we'll go through each of these one by one. So don't worry about getting the list down now. We're going to talk about each one on its own slide. First, we'll talk about volume versus pressure. When the volume of the container decreases, the gas molecules are getting smushed together more. So they're going to collide with each other and the walls of the container more often. That means that your pressure is going to increase. So I like to write this in shorthand because it helps me see it versus all the words. Decrease in volume means an increase in pressure. The opposite is true as well. If you have a container with like a cylinder in it, a piston, that you can change the volume, if you increase that volume, the gas molecules are going to have more room to roam around. So they're going to collide with the container less often, and the pressure will decrease. So for volume and pressure, we have an indirect relationship or an inverse relationship. If you increase one, you decrease the other. Let me know if we're good to move on to the next slide. Okay, we'll wait. And I'm just going to give you the warning now. We're probably going to have to take a break soon so I can feed my son. He's not bottle fed. He's mommy fed. So I appreciate your patience with me in advance. All right. The next variable that affects pressure is temperature. We hinted at this a little bit when we were talking about pressure and defining it. Now we're going to talk about this relationship directly. So when you decrease the pressure, when you decrease the temperature, the gas molecules are moving around more slowly. They've got less energy. So they're colliding with the container less often, not as forcefully. That means your pressure is also going to decrease. What that boils down to is if you decrease the temperature, the pressure will also decrease. If you increase the pressure, the molecules have more energy, they're moving around faster, they're colliding with the container more often and more forcefully, so the pressure increases. Increase in temperature, increase in your pressure. This is a direct relationship. Whatever happens to temperature will also happen to the pressure. Let me know when you're ready to move on. So I'm going to be grading exam 4 this week. it will be graded before classes are over. Like before you go home for Thanksgiving, all of your grades will be in. So I have one assignment from another class that is in front of your exam 4, and I'm almost done with that. Then I will start your exam 4. And thanks for reminding me of that, because I wanted to bring that up. So thank you, Talia. The exams that are not through Respondus take me longer to grade. So if some of you have your grades but some of you don't, that's why. It takes time to go through and look at all of the work that you've done and give you as much partial credit as possible. Alrighty. The last relationship we're going to talk about with pressure is molecules and pressure. Another way that we can talk about the number of molecules of something is how many moles, which in the world of gases is N. I know we talked about N in chapter 8, that's a different N. Here in chapter 10 with gases, when you see a lowercase n, that means moles. Let's say that you have a container and it's hooked up to a gas tank. So you can increase the amount of, gas in the tank at will. And you can maybe open a valve and release some gas at will. If you have the same volume, then you can increase the number of molecules and you'll increase the pressure as well, simply because there's more molecules. So I'll call that N. If you increase N, you increase the pressure. If instead you vent down that container to release some of the gas to the atmosphere, you're going to decrease the number of molecules in that chamber. Along with it, your pressure will decrease. This is another example of a direct relationship. So temperature and pressure, molecules and pressure have a direct relationship. What happens to one happens to the other. Pressure and volume, however, indirect. So the opposite happens. Let me know when you're ready to move on from this slide. Okay, everybody ready? Now we're not doing practice problems yet. We're going to focus more on the calculations in a little bit. And next week, whatever we don't get through from chapter 10, we'll finish. And then we'll do some more conceptual questions and things like that. So next week will be kind of a wrap up for chapter 10 and any other things that you guys might need. I know we normally do a lot of examples throughout, but we're first laying down the foundation. Then we'll get to some of the math. So we talked about pressure and some of the variables that affect pressure. Now we'll introduce the different gas laws. The first law we'll talk about is Boyle's law, which he came up with after doing this experiment, Boyle's gas experiment. Very original name, I know. So Robert Boyle used what's called a J tube, and it's literally a tube that's shaped like a J. And liquid mercury is great because it's very dense and it can act as kind of an air block. He put some mercury into this J tube and trapped air here and allowed atmospheric pressure to push down on the mercury, right? So we had 1 volume of mercury in the J tube. If instead he doubled that volume, then you have a change in the amount of air that's trapped. So if you start with 30 milliliters of air trapped, and you have a set volume of liquid mercury, which is what the gray stuff is, if you decrease that volume of mercury, you're going to increase the volume of air that you've trapped. So his law deals with pressure and volume. You don't really need to know about the experiment, but you do need to know the law. I can go back. You don't need to know details on the experiment per se, but if you just want it for completeness, go for it. Okay. So Boyle's law states that the volume of a gas is inversely proportional to the pressure at constant temperature. So constant temperature is the key here, okay? And we already talked about this relationship between pressure and volume. Robert Boyle is the one who discovered this relationship. The equation is P1V1 equals P2V2. P is pressure, V is volume. And whenever you see a subscript of 1, that means your initial conditions. And in these gas law questions, you're always given a set of initial conditions and some final conditions, and you need to calculate one of the final conditions. And that's what the Tues are, the final conditions. So if you started with a gas at pressure 1 and volume 1, and the pressure changed to pressure 2, what is volume 2? That's a very generic example of a Boyle's law question, which we're going to do a couple of those. This graph just shows you what an inversely proportional graph looks like. High pressure, low volume, which is up here. Low pressure, very high volume, down here. Let me know when we're ready to move on, because we're going to do a problem. We ready? Okay. So let's do an example. Just like in chapter 9, where you had to identify the type of problem first, it's the same thing with the gas law problems. You're not going to get a title that says Boyle's law problem, and you say, oh, well, I guess I should use Boyle's law. That's not how it works. So you need to be able to read the problem, pick out each piece of information, which is each number, and identify it. Is it a pressure? Is it a volume? Is it a temperature? And what am I asked about? And from there, you figure out which gas law makes the most sense to use to get to the answer. So that's what I'm going to show you here. I have another example after this that you can do. You can decide if you want to do one or not. But these gas laws are fairly simple. A 3.50 liter sample of methane gas exerts a pressure of 1,550 millimeters of mercury. What is the final pressure if the volume changes to 7.00 liters? We've got 3 numbers here. And we need to identify all of these. Anything that's got liters or milliliters is going to be a volume. And this first sentence describes what our initial conditions are. So this is our V1, the initial volume. And the 1550 millimeters of mercury is our P1, our initial pressure. What is the final pressure if the volume changes to 7 liters? That wording tells us that the 7 liters is the final condition for the volume, V2. We're being asked about the pressure. We don't know what it is. Since all we have is pressures and volumes, that must mean Boyle's law. Everybody good so far? Cool. So now we know what law we need to use, Boyle's law. You'll get these on an equation sheet for the final. So you don't need to memorize these, but I'm not going to tell you that this is Boyle's law. You'll need to recognize it. We need to solve this equation for P2. I like to circle the variable that I need to isolate because it helps keep me on task. To isolate P2, you divide by V2 on both sides. Now notice how I grouped the volumes together instead of putting everything over V2. This is because it will help you keep your units straight when you're doing the math. You don't want to give me a pressure in liters because that's not right. You group together your volume constants, your pressures, your temperatures, and that will just make your life a lot easier. Now you can fill in the numbers that you have from the problem. So P1 is 1550 millimeters of mercury. Our initial volume is 3.5. And the final volume is 7. When we do this calculation, the units from the volume cancel out. We're left with the units of pressure, millimeters of mercury. Before we put our calculator to work, let's think about what our answer should be. We're going from 3.5 liters to 7 liters. Is that an increase or a decrease in volume? It's an increase. Based on what we know about pressure and volume, what do we expect? An increase in pressure or a decrease in pressure? We should expect a decrease in pressure. Put this in your calculator and let me know what you get. It should line up with our logic. It should be smaller than the initial pressure. You can write it in the chat when you have your answer. And don't forget your units. millimeters of mercury. That's Boyle's law. So let me know if you want to do another one of these on your own or if you want to move on. Okay, we can do one more. I'll let you guys do it. This time we're changing the numbers up just a little bit. This time your volume is 7 liters for initially, and it's changed to 3.5 liters. So I will give you 2 minutes to set this problem up, and then I'll start writing it out. And I'll start writing it up here since we got an answer already. So that's what it should be. Now, if I wanted to be a stickler for sig figs, we need to have 3 sig figs here. To do that, we'd have to write it in scientific notation. But I'm not going to do that to you. It's just a reminder. Don't forget about sig figs or scientific notation. So how's Boyle's law? We good on it? All right. Let's move on to the next law. This is Charles's law. And he looked at volume and temperature. Volume and temperature are directly proportional, which means if you increase the volume, then you increase the temperature, and vice versa. The temperature, however, has to be in Kelvin. Oftentimes, these problems will give you the temperature in degrees Celsius. You will need to convert to Kelvin. You take the temperature in degrees Celsius and add 273. If you need to go back to Celsius to report your answer, you take the Kelvin and subtract 273. That's a throwback to when we did temperature conversions in Chapter 2. The law, in terms of the equation, is a proportion. V1 over T1 is equal to V2 over T2. In its current state, not exactly helpful. So you'll need to cross multiply before you can do anything with it. On the equation sheet, you will get what you see here. V1 over T1 is equal to V2 over T2. You'll need to know that you need to cross multiply. What I mean by that is you multiply V1 by T2 and V2 by T1. Now that you have that, you can choose whatever variable it is that you need to solve for and work it out. You ready to do a problem? Let's do a problem. Oh yeah, balloons. I always forget about this slide. Liquid nitrogen is great to play with. I shouldn't say that, but it is. Only if you know what you're doing and you're supervised. If you pour some liquid nitrogen on a balloon, you'll see it shrink. It'll also get very, very cold, and it may get crinkly enough and rigid enough to where you can literally rip it in half. If you've never seen it, you should. Now we'll do a problem. We have a 132-liter helium balloon that's heated from 20 degrees Celsius to 40 degrees Celsius. What is the final volume at constant pressure? Always start by writing out all of the variables that you're given. And that will help you identify which gas law you need to use. This first sentence tells you the initial conditions. 132 liters, that's a volume. We'll call it V1. 20 degrees Celsius is a temperature, and it's the initial temperature. 40 degrees Celsius is another temperature. We'll call it T2. We're asked what the final volume is, so we don't know. When all you see is volume and temperature, that means Charles's law. To use Charles's law, you have to do the cross multiplication first. And if you feel comfortable, go ahead and work ahead of me, and you can put an answer in the chat for what the final volume is. We're solving for V2. So that means you're going to divide both sides by T1. Notice how I group the temperatures together. It will make your life easier. Now you can plug in the values from the equation, or from the problem. We have 132 liters for our initial volume. Don't forget, these temperatures are in Celsius, so we need to convert those to Kelvin. In Kelvin, if you just add 273, then you get 293 Kelvin for T1. And you get 313 Kelvin for T2. If you're afraid that you're going to forget to do that conversion, as you're writing down the initial information, just convert all your temperatures to Kelvin before you even start figuring out which gas law you need. If you don't convert to Kelvin, you will not get the correct answer. So if you haven't already, try putting this into your calculator and see what you get. That's what I get to, 141 liters. Let's make sure that makes sense. Charles's law says that there's a direct relationship between volume and temperature. We're going from 20 degrees Celsius to 40 degrees Celsius. So we're increasing our temperature. The relationship says that we should see an increase in volume. And when we look at the math, that's what we see. The initial volume was 132 liters. The final volume is bigger, 141 liters. Do we want to do an example, or do you want to move on? We got to vote for move on. Okay. So I have another example here. I'll fill it in before I post the PDF of the notes. The third gas law we're going to cover is Gay-Lussac's law. And he looked at pressure and temperature. Of course, the temperature is again in Kelvin. These two are also directly proportional. So if you increase the pressure, you increase the temperature, and vice versa. Gay-Lussac's law looks suspiciously like Charles's law. Since they have the same relationship, pressure and temperature, as volume and temperature do, they look pretty much identical. The same rule applies where you need to cross multiply before you can actually have something usable. Once you have that, you could solve for whichever variable you need and then fill in your numbers from the problem. Ready to try a problem? I'm going to let you guys just try it straight up because it's so similar to Charles's law. So you've got a steel container of nitrous oxide at 10.4 atmospheres. You cool it from 33 degrees down to negative 28 degrees Celsius. What is the final pressure at constant volume? So I will let you do this one. I'll give you a 2-minute head start. Put your answer in the chat if you get to an answer. But after 2 minutes, I will start writing out how I solved the problem. Let me know if you get stuck. I'll start writing out the problem here. So we've got all pressures and temperatures. Has to be Gay-Lussac's law. We'll just have to wait and see. You do your cross multiplication, and we are looking for P2. Now, if you haven't already by this point while you're working out the problem, make sure that you convert your temperatures to Kelvin. Otherwise, you will not get the right answer. We substitute in our numbers. And you should get 8.33 atmospheres. I always encourage you to check and make sure that the answer makes sense with these simple gas laws, because you can do the logic check and make sure you didn't punch something into your calculator wrong, like flip, it's supposed to be T2 over T1. Maybe you put T1 over T2 instead. That would give you a different answer. So here we went from 33 degrees Celsius to negative 28 degrees Celsius. That's absolutely a decrease in temperature. One that I find offensive personally. If you decrease the temperature, well, the pressure and temperature are directly related. So you should see a decrease in pressure as well. It takes an extra second, but it really will save you some points if you put something into your calculator wrong. If that logic doesn't add up with your answer, you should revisit it. So how do we feel about Gay-Lussac's law? Do you need another example, or do you want to move on? All right, we got to move on. So like I said, I'll put the answer to that one there. We can combine all of these gas laws together. And it looks like this. P1 V1 over T1 is equal to P2 V2 over T2. You're going to need to cross multiply just like before, and I'll show you. So let's say that we want to solve for V2. I went to this slide real fast. Did y'all need a second to write down what the combined gas law is? Because that's what it is right there. I'll go back. That's literally all that's on this slide. Let me know when you're ready. So let's say that we want to solve for V2. Make sure you do your cross multiplication first. Then you can solve. So you're dividing by P2 and T1 on both sides. When you write this out, group your terms together. The only tricky thing here is making sure that you keep the subscripts correct. So flipping P1 and P2 or T1 and T2, it's very easy to do here. But as long as you are good with your bookkeeping, you should be good to go. Do you need me to show you another example of how to solve for a variable, or do you think you're good? All right, we'll do another one. Let's say this time we want to solve for T2. Instead of multiplying by something, well, we sort of kind of are. You're dividing by P2 over V2, which looks like this. You can also, so I moved ahead of myself a little bit. So you can do it straight like this. Might be a little bit more difficult if you're not good with math. You can also do the cross multiplication first. And then solve for T2. This way is easier, but you'll get to it the same way, no matter how you do it. So that's how you would get to T2. For each of these combined gas law problems, you'll have to figure it out each time, which one to use. We ready to try a sample problem? So let's say that you have 10 liters of carbon dioxide gas at 300 Kelvin and 1 atmosphere. If you double the volume and you double the temperature, what is the new pressure? Yeah, I think the numbers might help. So the question gives us the volume and the temperature, the new ones, but we just have to do the math. So double the volume would mean 20 liters, and double the temperature would mean 600 Kelvin. We don't know what the new pressure is, that's what we're being asked. But when you see all three of these, pressure, temperature, and volume, that's the combined gas law. We're solving for the new pressure, so we're going to cross multiply first. P2 is what we're after. So you divide everything on both sides by V2 and T1. Now you put in your numbers. In these gas laws, it doesn't matter what the ones that we've gone over so far, doesn't matter what unit your pressure is in, your volume. The only thing that matters is that you have your temperature in Kelvin, and that if you have a initial volume and a final volume, they need to be in the same units. So you can't have liters on one side of the equation and then milliliters on the other. So what you actually end up with for P2 is that the pressure has not changed. It's 1 atmosphere. Now you can't do the same trick that we had been doing where you check your logic. Because if you're changing one thing by some, the volume is going up some, but the temperature is going down a little bit, you can't make a prediction as to which one is going to have more weight. You just have to do the math. But is this a little bit more clear now how to use the combined gas law? Okay. Uh-oh. That's baby boy Hefner. So that means it's time for a break. We're going to take a little bit lengthier of a break this time. So Mama Hefner needs about 30 minutes. Then we'll get back to it. So 3:40, I'll see you back here. Don't complain all at once. I know the long break is such a sad shame. All right. All right, that was a little bit of a lengthier break than normal. But thank you for your patience. We left off with the combined gas law. Are there any questions? Okay. So, I had planned to do more of these types of questions next week. We'll have time to do kind of a problem-solving session for Chapter 10. We're going to add on a couple of more concepts, and then we have one more, I guess technically 2 more gas laws to do. So we talked about atmospheric pressure. Now we can talk about vapor pressure. Every liquid, if you put it in a container, and it's a closed container, over time, you're going to build up vapor. And that vapor will exert pressure on that closed vessel. At every temperature, you have a different vapor pressure. As the temperature increases, vapor pressure increases. Which kind of makes sense. That's kind of its own little nugget of information about vapor pressure and the concepts there, right there. Yeah, I can go back. But just knowing that vapor pressure, it's the pressure of the vapor above a liquid. Okay. And this is another kind of gas law. This is Dalton's law of partial pressures. It's not really a gas law per se, like to talk about relationships between, pressure and volume or anything like that. But it does talk about the total pressure of a mixture of gases. Let's say that we bring up our scuba diving example again. Again, that would never be me. Nope, don't trust it. But if you do, you're going to have a tank of gas so that you can breathe. And there's different mixes of gases that you can get. It's going to have some oxygen. It will also have some nitrogen. May have some helium as well. And for the purposes of this example, let's say that you have this mixture. In the tank, each of those gases is going to exert a pressure on the walls of the tank. The total pressure, which we'll call PT, is the sum of the pressure from all of those gases. So the pressure of the oxygen gas, plus the pressure of the nitrogen gas, plus the pressure of the helium. That's all that Dalton's law is. The total pressure for a mixture of gases is equal to the sum of all the individual pressures of each gas. We good so far? The next slide up is a problem, so just a quick partial pressures problem. So let's try a problem. This is a very simple problem, okay? But I'm going to point out several things along the way that you'll want to look out for. Uh-oh, screen just went black. We'll wait for it to reconnect. The day was going so good, too. Blackboard was cooperating and everything. So we'll just wait for it to reconnect. And when it does, we'll do a sample Dalton's law calculation. Alright, screen should be back up. Thanks, Blackboard. You're a real one. Perfect timing. Okay. So we're talking about Dalton's law and how the total pressure in a container that has a mixture of gases is simply equal to the sum of all the partial pressures of each gas. In this problem, we have a sample of noble gases: helium, neon, argon, and krypton. We have all these different partial pressures for each of them, and we have to figure out the total pressure of the sample. The total pressure is going to be equal to the pressure of the helium plus the pressure of the neon plus the pressure of the argon plus the pressure of the krypton. Now, one word to the wise here. This is a pretty simple question. You just have to add a bunch of numbers together. But one of the gotchas here is that I could give you pressures in different units. So I could tell you millimeters of mercury for one gas and atmosphere for another. And you will need to recognize that and either change one to the other unit so that you can add them together. So it's not a complex problem, but it's one where you have to pay attention to your units. Here, everything is in millimeters of mercury. So we've got 125 millimeters of mercury, 45 millimeters of mercury, 158, and 17. If we total all those up, it'll give us the total pressure of that sample. You can put it in your calculator if you'd like, but I'm pretty confident that you guys can, you know, add together some numbers. But if you do it, you should get 345 millimeters of mercury. Any questions here? Okay. We're going to do one of those next week. We're going to do one of the ones where you have to convert. So next week is going to be a problem solving session. Okay. And I'll also post practice problems like I usually do. So you'll have practice in both ways. Related to partial pressures, there are some experiments where you're collecting a gas over water. So let's say that you add zinc to an acid like sulfuric acid, and you want to collect the hydrogen gas over water. You're going to have a mixture of hydrogen gas and water vapor because each liquid has a vapor pressure. You're going to have some amount of vapor from the water in the sulfuric acid solution that is commingled with your hydrogen gas. When you collect gas like this, it's called wet gas, since it has water vapor in it. There's a way that we can calculate how much of that gas is water versus the sample we're interested in. That's using this table. This table you do not need to memorize. It will be provided for you. If it's not the whole table, I'll at least give you the little snippet of information that you need to solve the problem. All this table contains is at each given temperature, starting at 5 degrees Celsius, going all the way up to 100 degrees Celsius, it tells you what the vapor pressure of water is in millimeters of mercury. So if we were at 25 degrees Celsius for our experiment with the zinc and the sulfuric acid, then it would be 23.8 millimeters of mercury. And that's just the water. So using that partial pressures from Dalton, we can figure out the pressure of the hydrogen gas. We've got the water vapor, which is the pressure from the H2O. And this is our gas sample that we care about, that we collected. We can rearrange here. And we can solve for the partial pressure of the hydrogen gas. Does that concept make sense? This is collecting gas over water and how you can figure out what the partial pressure is of the gas you're interested in. So let me know if that makes sense. Yeah, I can repeat that. And we have an example. We're going to actually do a calculation. So let's go forward one. we're going to do an actual problem. And it's the same idea of collecting gas over water. So a sample of hydrogen gas was collected over 20 degrees Celsius water. The atmospheric pressure is 755 millimeters of mercury. What is the pressure exerted by the hydrogen gas in the cylinder? So we know that we have a sample of wet gas, which means the total pressure is the hydrogen plus the water vapor. Using the table that I showed you, you can look up what the partial pressure is for water at 20 degrees. So this you would get from the table. The total pressure is going to be equal to the atmospheric pressure, which we're given. So if we rearrange this partial pressures equation to solve for the pressure of the hydrogen gas, you subtract the partial pressure of the water from the total. To put our numbers in, the total is from the problem. That's our atmospheric pressure. The pressure from the water we looked up in the table, and that's 17.5 millimeters of mercury. To get the difference, or you get the difference, and that tells you what your partial pressure is for the hydrogen. But we have to remember our sig figs. This time we're subtracting, and adding and subtracting, the rules are a little bit funky. Your calculator will tell you 737.5, but you have to remember you can only report up to the ones place. With adding and subtracting, you can only have as many places as the number with the fewest places. So 755 doesn't have anything after the decimal. So we can only have 3 sig figs here. So it should be 738 millimeters of mercury with sig figs. Not too pressed about the sig figs at this moment. I want to make sure that you understand the concept of collecting a sample of gas over water. So does the example help? And we'll do some more examples of this next week that are a little bit more complicated, and we're going to be combining some concepts here. So now we're at a crossroads. The other section of Chem 103 that I teach only got this far. We have another 30 minutes. We can very likely finish this chapter. Do you want to press forward and finish the chapter? Or would you like 30 minutes added onto your life today? Makes me know, never mind. So let me know in the chat. Keep going, or 30 minutes added. I won't be offended either way. 2 votes for 30 minutes added. I ain't mad at you. If y'all are cool with that, we can end it here so that everybody's in the same place. So you're welcome. It's an early Thanksgiving miracle. You get an extra 30 minutes added back to your life today. Praise him while you can. So we will get back to it next week. I'll give you a chapter 10 video. I'll just very quickly go to the last slide, which is the reminders. So chapter 10, thank you. Chapter 10, don't forget you do have homework due on November 22nd. There's no chapter check-in, and you do have a final exam for this class on December 8th, which is a Tuesday. You have to log in and start your exam somewhere between 2 and 4 p.m. and you'll get 2 hours. We'll talk about that next week, but I just wanted to hit you with those reminders. All right? Get started on your Master in Chemistry. We'll finish up Chapter 10 next week. If you have questions for me, go for it. Otherwise, enjoy that extra 30 minutes to your day. Be safe.